Hello everyone, my name is Arohi and welcome to my channel. So guys, in my today's video we'll understand what are vision transformers. So vision transformers were first introduced in this paper, and images worth 16 into 16 words transformer for image recognition at scale. So this was the first paper where transformers were used for computer vision tasks. So if you'll scroll down, you can see the model architecture of vision transformer. This is the architecture. So in my today's video we are going to understand the vision transformer architecture layer by layer, and it will be in detail. So guys, I have already done one video on vision transformers, but in that video we understood the whole vision transformer layer architecture briefly, right? But today we are going to focus on each and every layer, and we'll see each layer in detail. So for example, if we talk about this encoder layer only, so in this encoder layer we have multi-head attention layer, right? So we'll understand the concept of multi-head attention layer in detail, like what is query key and value, how we get those value, what is the maths behind it, how we perform query key and value, how we achieve those values for query key and value, right? So like this, for each layer we will understand the concepts in detail. So let's start. So this is the layer architecture of vision transformer. Let's understand every step one by one. So the first step is this. So what we are doing over here, we are dividing the image into patches. Now let's understand how we divide the image into patches. So for that, scroll down and here you can see. So guys, here I'm explaining you this concept with the help of example. So suppose we have input image. So this is our input image, and when we divided this image into patches, this is how our image looks like, right? So here you can see these small boxes. This one box, this is a single patch, this is one patch, okay? So this is a different patch, here is a different patch. So each square box over here is a patch. So how many patches we are having over here? So how do we know that? So for that, let's scroll down a little bit and let's understand over here. So suppose our input image is 224 into 224, okay? So the height and width of this image is 224 into 224, and the patch size we have is 16 into 16. What it means is this single patch over here, the height and width of this patch is 16. So like this, each and every patch in this image is of size 16 into 16. And number of patches, how many patches we have? So how do we know that how many patches we have on this image? So for that, you divide the image size with the patch size and you'll get this number. So 14 into 14. So we have 196 patches. Okay, so how many patches we have on this image? 196. So if you want to count, you can see this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So we have 14 patches horizontally and we have 14 patches vertically. If you multiply, then you will get the number of patches on this image. So we have 196 patches, and the stride we have used over here is 16. Now guys, what is stride? Stride simply means how much jump your sliding window will perform each time. So suppose here was your sliding window, okay? So stride 16 means it will jump from here and it will come here, and then from here it will jump again 16 pixels and come here, and then third time it will skip 16 pixels again and it will come here. So stride 16 simply means how much jump your sliding window will take. This 16 means 16 pixels. Okay, so when stride and patch size is same, it simply means that each patch in your image will have different data. Okay, so see guys, these values which I chose over here, this image size, this patch size, and then this stride, so these are the values which were used in the original paper. This paper's images were 16 into 16 words, so we are using the same values over here. So when your image is 24 into 24 and patch size is 16 into 16, how many patches you'll get? You'll get 196 patches. So this is the first step. So if you'll see this architecture again, so what we have done, we have divided our image into patches, and now we have 196 patches. In this example, how many patches image is divided into? How many patches? 9 patches, right? So in our case, we have 196 patches. Now once you divide your image into patches, next step is to convert those 2D patches into 1D vector. 2D patch simply means, see, this is the first patch. If you'll see here now, this one, this patch I have shown you over here. So this is a 2D patch. 2D patch simply means it has height and width, right? And the height is 16, width is also 16. So 16 into 16. So the patch is this. So in first patch, what data is there in the first patch? What feature is there in the first patch? We can say that first patch contains the feature of sky, right? So if you'll see, now let me show you one more patch. Okay, so over here the patches are too small. Let's say if we want to see this patch, we will enlarge this patch now and we will see it. So this is the patch number 43, this patch. Okay, this patch, when I enlarged it, so this is how it looks, and here you can see that the pixels which are over here, these pixels are green in color because these pixels are storing which feature? Grass, right? And the pixels which are over here on the top, these pixels are storing which feature? The sky, right? Now what we want is our patch size is 16 into 16 and all these patches are colored patches. That means into 3 is a channel RGB, right? So our input image, this image is a colored image, so it will have 3 channels, right? R, G and B, red, green and blue. In the same way, the patches which we have on this image will also have 3 channels R, G and B. So 16 into 16 into 3 is 768. Okay, what is this 768? We flattened this patch and we got 768 pixels in single line. So this is a flattened, this is our flattened patch. Flattened patch means now we don't have height and width of it, we have single patch like this, and this single patch have how many values it has? 768. And how we got the 768? Because when we multiply the 16 into 16 into 3, we got 768, and these 768 means the 768 different values. Okay, now let me show you how this flattened patch look like. So okay, before that we have how many flattened patches now? How many flattened patches we are going to have? 196. Why? Because we have how many 2D patches we have? 196, and when you will flatten all those patches, you will have 196 flattened patches, and each flattened patch have how many tokens? 768. Tokens simply means pixels or values. Okay, so each flattened patch have 768, you can call it tokens or pixels or value. Now let me show you how these flattened patches looks like. So this was our input image, right? And this is the patch number 43, this patch. And for this patch, this is how the flattened patch looks like. See, here you will see that at the end you have greenish areas, right? In the starting you will see the bluish areas. So first few pixels are blue in color, right? So in the starting till here, starting from here till here we have these features, okay, and after that we have these features, and all these features are, all these pixels are present in single line. And guys, here you'll note the small squares. These small squares are pixels. One square means 1 pixel, this square means 1 pixel, this square means 1 pixel, okay. So this is how our flattened patch look like, and if you want to see the values in it, the values in that flattened patch looks like this one, okay. So how many values we have over here? In this area we have 768 values. Now guys, let's try to understand what these values are, what is the meaning of these values, okay. So as I've told you that these are RGB patches, right? RGB means colored patches. So colored patches means you will have some value of R, you will have some value for G, and you will have some value for B channel also, okay. For each pixel, let's talk about this pixel. For every pixel you will have 3 values. So 3 values means 1 value for R channel, 1 value for G channel, and 1 value for blue channel. Now let's talk about this first pixel over here. So for this single pixel, how many values you are going to have? 3 values. Now here you'll see these 3 values, the values which are in yellow color. So the first value is the value for R channel, second value is the value for G channel, and third value is the value for B channel, and these 3 values belongs to the first pixel. So what is the value for R channel? 152. And what is the value for green channel? 192. And the value for blue channel is 228. So guys, now if you'll see these 3 values, you will find out the value which belongs to blue channel is higher as compared to the value which are there for red channel and green channel. Now why? Because if you'll see the first pixel over here, we can see with our eye, and we can simply say that this is this pixel have blue color, right? So the intensity of blue at the first pixel is high. So guys, these three values are simply the intensity of those colors for that particular pixel. So what I'm trying to say is that the intensity, so always the intensity for this red, green and blue channel will lie between 0 to 255, okay. So you'll see this side that all the values are between 0 to 255, okay. Why? Because the intensity for red, green and blue color always lies between 0 to 255, and the higher the value means that pixel have that color the most. For example, 0 means the least amount of color present at that pixel, and 245 or 250 means that for that pixel the intensity of that color is high, the color is present over there, okay. So for example, in our case, the intensity for blue color is 228. So we can say that at first pixel over here, the intensity of blue is more, right? And guys, always remember, whenever you work with whenever you work with colored images, so you will always get 3 values for each pixel, and the combination of those 3 values will give you the color which you see at that pixel. So this blue over here is the combination of these 3 colors, okay. Now let's see this value over here, this one, 80, 104 and 88. First value always belongs to first channel, which is red. Second value is 104, right, which will be the value for green channel. And then the third value is 88, which belongs to the blue channel. Now you see, so these three values we picked from the last line, and if you'll see that in last lines what we have green color, the greenish pixels are there, right? So here you'll see the value for green is higher, the intensity of green color is higher as compared to the intensity of blue channel and the red channel. So by looking at these values only, we can say that the at this particular location the pixel is going to be greenish in color, right? So this is how we get three values for each pixel, and that's how we get this 768 values when we flatten 16x16x3 patch. Okay, so this is the second step. Now what we have after performing this step, what we have now, we have 196 flattened patches, right? Now we have 196 flattened patches, and the size of each patch is, how much is the size? 768 tokens, right? Now we have 196 flattened patches, and each patch have 768 tokens in it, 768 values in it. And for each patch, this kind of flattened patch you will see, and 196, all the 196 patches are going to have these kinds of 768 values. So this is how your flattened patch looks like. This is how your 2D patch looks like. This is how your flattened patch looks like, and these kind of values you are going to have, and all these values are going to lie between 0 to 255. Right, clear? So this was the second step. Now what we have done till now, so if you'll see here, we have performed this step, we have divided the image into patches, and after that we flattened our patches. Okay, we have performed till here, and the output we have over here is 196 patches, and each patch have 768 values. Okay, now let's see the next step. What is the next step? It is linear projection of flattened patches. Now let's try to understand what is happening over here. So the input to linear projection is the output of the previous layer. What is the output of the previous layer? This is the output of the previous layer, and what we got from here, we got 196 1D patches, and the size of each patch is 768, right? So this will be the input to the linear projection layer. Now guys, at linear projection layer, this is the formula which we are going to use for each patch. Okay, for each patch we will use this. Now what it is, let's understand. So y means, what is y? Y is output we want, right? The output which we want from linear projection layer is y. And what is x? Our x is 196 1D patches of size 768, right? This is our x. Now what is our w and what is our bias, and how we are going to calculate this? Let's try to understand that. Before moving to that step, guys, one important thing to tell you, what is the benefit of linear projection? Why we are performing linear projection over here? What is the need of it? What is the benefit of it? So with the help of linear projection, we want to reduce the dimension of the 1D vectors for each patch. So right now we have 196 1D patches, right? And each patch have 768 values in it. This is what we have. Now what we want is, we want to reduce it to 512. Now we want 196 patches, and each patch should have 512 values. What will be the benefit of doing it? Why we want to reduce the values from 768 to 512? Now let's try to understand it. So the first benefit is, when you reduce the number of values, let's see the vector again. So this is how our 1D vector looks like when there are 768 values in it, right? So if you reduce the number of values in this vector, what will be the first benefit? First of all, you will have less number of values. That means less memory is required because the number of values are less. So that means the memory usage will be less, right? And second benefit is, if there are less number of values, that means processing will be fast because now the values are less as compared to the previous one. Now let's say if we reduce it to 512, earlier the values were 768 and now the values are 512. So obviously the resources which are needed when we were processing 768 values were more as compared to the resources which are required to execute the work on 512 values, right? So these are the two benefits. First is less memory and less computation. Another benefit is, when we are reducing the number of values from 768 to 512 in each patch, at that time we are only storing those values or those pixels which are having important information, and we are discarding all the noise or all the unimportant pixels, right? So these 512 values which we are going to have after the linear projection layer will be the refined values. Those values are going to have all the important information. Nothing is going to be lost while reducing the size of the dimension of the patches, right? Because the linear projection layer works in a way that all the important information for each patch is going to be stored in those 512 values. Okay, so this is the benefit. Now we are going to have the refined 512 values. We have removed all the noise from the patches. So this is the benefit of linear projection layer. Now how to perform linear projection layer? Let's see that. So guys, as I've told you, for each patch we are going to execute this formula. Y is the output of the linear projection layer. What will be the output of the linear projection layer? The transformed feature. We will have transformed vector for each patch, right? And what will be the transformed patch? What we are saying is, we want 196 patches and the size of each patch should be 512. Earlier it was 768, but now we want to transform each 1D vector of all the patches to this size 512. Now let's understand it through this picture. For each patch, what we will do? We will perform this. Y equals to Wx plus B, where x is the input. What is the value of x? This is the neural network, okay? So this will be, at linear projection layer we are using a fully connected neural network, okay? Fully connected neural network we are using at linear projection layer to transform the features from 768 values to 512. So the input to this linear projection layer is this first layer. Is what is this layer? This is our input layer, okay? And the last layer is our output layer. What is the input to linear projection? The output of the previous layer, which is 196 patches of 768 values. Okay, now each patch will go to this neural network one by one. These two are the hidden layers. Okay, these are hidden layers. Now guys, how many neurons we have in the input layer? So we have 768 values in all the 1D vectors of 196 patches. So we have 768 neurons in our input layer. And the output layer, how many, what is the dimension we want in the output layer. So as I've told you that earlier we have 768 values in each patch, and now we want to transform it into 512 values. So the output 1D vector for each patch should have 512 values. So this output layers have how many neurons? 512 neurons. Okay, one neuron will store the value, one value. So we want 512 output values for each patch. So that's why we have 512 neurons in the output layer. And in between, these are the hidden layers, and you can have as many neurons you want as per the problem you're working on. And each neuron from the previous layer is connected to each neuron to the next layer. This is what neural network is. So this kind of neural network is used at linear projection layer. If we go back to this formula again, x w plus b, right? So we know x is a single patch, okay, one by one. So for each patch we are going to execute this functionality. So the x is, how many values are there in one patch? 768 values in one patch, right? So this is the value for single patch. And then the output we want is, what is the output we want? We want to have 512 values for each patch. This is the output we want. Then what is the W? What will be our weight matrix? Weight matrix will be 512 into 768, means you're going to have a matrix, weight matrix. This weight matrix, initially we will have some random values over here. Initially we'll assign some random values, and then these values will be learned when we will use this neural network. After every epoch we will calculate the loss, and then we'll update the weight values, right? This is how neural network work. So 512 means vertically you are going to have 512 values, and horizontally you are going to have 768 values, and initially you will put some random values over here, and then slowly epoch wise epoch, using this neural network these values will be learned, and then we will get the output. Over here we will have output where all the 196 patches will have the values 512, and this means how the output will be arranged over here. So y1, y2, y1 is first patch, y2 is second patch, y3 is third patch. Like this you will have y196, because we have 196 patches now. So you will have all the 196 patches over here, okay? You will have all the 196 patches, and each patch, this patch, this patch, this patch, and all the patches are of this size now, 512 into 1. Okay, so this will be the output of the linear projection layer. Now let's try to understand the concept of this linear projection with example. Let's see how we are going to use this weight matrix and how the values are going to be calculated. So for that I'm using a simple example. We are not using the example where we have 196 patches and each patch is of size 512. Okay, so I'm going to use a simple example. Suppose we have one patch, and that patch have 10 values, and this patch is the input to linear projection. Okay, so this is what we are going to use. What we are doing, we are using a one patch which will have 10 values. Instead of having 768 values, I'm showing you the example with 10 values. So you can see here, suppose this is my 1D patch, and this patch have how many values? 10 values. Now I want to use linear projection on this patch, and instead of having 10 values, now I want to have a 1D vector with 6 values. Okay, we want to reduce the size from 10 to 6. So this is the weight matrix. So remember, I've told you here that we are going to have a weight matrix, and initially we will put some random values over here. So this is my weight matrix. Okay, this is my weight matrix, and on this direction we have 6 values, and on this direction we have 10 values. And how we got that? Our x2 linear projection is 10 into 1, and the output we want is 6 into 1. So our W will be 6 into 10. So this is my weight matrix, this over here, and we have some random values initially. These values will be learned once we start the training. Forward pass will happen, and then in backward pass weight values will be updated on the basis of the loss, right? So these are the random values. Now this value, so this formula we want to apply, W x plus b. So first I'm showing you this part. So this is my weight matrix and this is my x. Now we want to multiply it. For the first value, this value, here I have shown the process. See, this 0.1 into 1 plus 0.2 into 2, 0.3 into 3, 0.3 into 3 plus 0.4 into 4, 0.5 from here into 5. So this is how you will perform the multiplication and you will get this value. Now for y2, y2 is this 0.2 into 1 plus 0.1 into 2, 0.4 into 3, 0.3 into 4, like this you will calculate the y2, and in the same way you will calculate this y3, y4, y5 and y6, and I have shown you for y6 also. See, 0.6 into the first value of x, 0.5 into the second value of x, right? So this is how you will calculate. This is the first value, second value, and this is the sixth value. And when you will perform this, when you will perform w into x, when you will multiply this, you will get these values. See, these are the 6 values we have now. Earlier we were having 10 values, but now how many values we are having? We are having 6 values for each patch. Okay, now we want to add bias in it. See, we are adding bias, and the bias is 0.5. Here we have defined the bias also. See, here is the bias and the value of bias is 0.5. Now once you multiply w into x, we will add the bias in it, and this is the final 1D vector with 6 values you will get. So this is the transformed 1D vector which have 6 values for each patch. Okay, so this is the task of linear projection layer. Now you know how linear projection layer works. So in our case, the example we were using earlier, there we were having 196 patches, right? And we were having 768 values in it, but after applying linear projection, we wanted to have 196 patches with size 512, and for that what will you use? You will use this process, the process which I have shown you over here, right? So this is simple. This fully connected neural network is used for this task. So guys, this is how you perform linear projection. Now we have this output from the linear projection layer. Now the next task is position embedding. So if you'll scroll up and if you'll see the architecture, see, now after this layer, what we have now, the output of this linear projection layer is 196 patches, each of size 5 and 2. So how we started this task? At first step we were having image of size this, then we converted that image into patches, and then we have 196 patches, right, of size 16 into 16 into 3. Then we flattened those patches, then we have 196 patches of size 768, right? And after that we used linear projection. After that what we used? We used linear projection, and after performing linear projection we have 196 patches of size 512. So this is the input to this patch plus position embedding. Now this is what we are going to perform. Now what we want to do, so this 196 into 5 and 2, this will be the input to this part, and now we are going to, what we are going to do, we are going to add patches with position embedding. Now let's try to understand what is position embedding and how we are going to add position embedding with patches, and why we need this step. What happens at this step? What is the need of this step? So now let's understand what is the need of position embedding. So guys, let's understand this concept with the help of example. I'm using a different example over here. So suppose you have this input image. Suppose this is the input image and we have these 4 patches, 1, 2, 3, 4. See guys, entire image is divided into patches, but for the explanation's sake I'm using 4 patches so that you can understand the concept in a simpler way. So suppose you have 4 patches, so we are naming these patches. So this patch I've given the name cat head, and this patch is cat body, this patch is rug, and this patch is wall. So suppose we have these 4 patches. Okay, now what is the need of this position embedding? Why we want this position embedding? This is what we are going to understand. So guys, see, the output of this part will become the input to the encoder, transformers encoder. Till now, whatever we have done, we are not using transformer yet. So the output of this patch plus position embedding will become the input to the vision transformer. Okay, till now what we are doing, we are just preparing the input in the format which the transformer model accepts. Okay, so before giving the input to the transformers, we apply position embedding with it. And why we need it? Because guys, the encoder which is over here, the encoder of the transformer, what it does is it takes all the patches at once. Okay, so suppose if you have 4 patches in an image, so all those 4 patches will go to the encoder at once. So in our case, earlier we were working with 196 patches. So that means all those 196 patches will go to the encoder at once. So what will happen if all the patches will go to the encoder at once? The problem here is that encoder will not know which patch should come at first position and which patch should come at the second position and which patch should be in front of which patch, right? Our encoder will not understand the sequence of those patches. So to make your encoder understand the sequence of the patches so that it can understand the image properly, that this is how these patches are aligned, okay, to make a proper image. So we send the position of each patch with that patch. Okay, so for all these patches, for this patch we'll send the position of this patch. With this patch we will also add the position of this patch. With this patch we will add the position of this patch, and for this patch also we will send the position of this patch. What will happen with that? So now when all these patches will go to the encoder at once, your encoder will know from this position that where this patch is actually there on the image. Okay, so that's why position embedding is important, because then only your encoder will understand the sequence of the the patches, then only it will understand which patch should come first, which patch should come in between, and which patch should come at last. Okay, so that's why position embedding is important. Now let's try to understand the concept of position embedding. These are the important things which you need to know when you are performing position embedding. So the first thing is, how many number of position embedding vectors are required? See, these positions over here, these are also going to be a 1D vector. Like suppose these kind of values are going to be there. Okay, for each position embedding vector, you are going to have some sort of values like this. Okay, so now the question is, how many these kind of embedding vectors are required, position embedding vectors are required? So guys, it always depends upon the number of patches. So if you have 196 patches, let's say, as we were using this example earlier, so we were having 196 patches, right? Now we want to tell the encoder about all those 196 patches, right? We want to tell the position of all those 196 patches. So that means you are going to have 196 position embedding vectors. So the number of position embedding vectors are equal to the number of patches. So if we talk about this example over here, we have how many patches we have? So let's say if your image have 4 patches, that means we want to tell the position of these 4 patches to encoder. So in that case, you will have 4 position embedding vector, each vector for one patch, one position embedding vector for one patch. If you have 200 patches, you are going to have 200 position embedding vectors. Okay, now the second question is, now we know that we need 196 position embedding vectors, or in this case, if we talk about this image, so we can say we need 4 position embedding vector, right? Now what should be, we know that we need 4 position embedding vector, right? Now how many values are going to be there in these 4 position embedding vector, right? If it is a vector, there is going to be some values in it. Now how many values are going to be there in each position embedding vector? So that depends upon the size of each 1D vector. So the output of linear projection layer is 196 patches of size 512. So there are 512 values in each patch. So this 512 value is going to be the size of each position embedding vector. For each pixel, you are going to have one position embedding vector's value. Okay, so this each position embedding vector, how many values are going to be there? You are going to have 1, 2, 3 and 512 values for each vector. Okay, so I hope this is clear. Now next question is how we add the position embedding with patches. Right, now we see this. So what is the step happening at this place? What we want to add the patches 1D vector with the position embedding vector. So now let's try to understand this. So let's say here we will take one example. Okay, so suppose you have a patch, and in that patch you have this value 1.0, 2.0, 3.0 and 4.0. So for the simplicity purpose, for just to make you understand the concept, I'm using these 4 values. You just assume this is our 1D vector. This is our 1D vector of patch when we flatten that patch. Okay, this is what we have. Now position embedding vector, how many values are going to be in the position embedding vector? The number of values we have in a patch. So we are going to have 4 values in a position embedding vector. So let's say you have 0.1, 0.2, 0.3 and 0.4. Okay, so the values in both the vectors should be same. Now we will perform element wise addition, means you will add this with this, this with this, this in this, and this in this. So you're going to have a final vector like this: 1.1, 2.2, 3.3 and 4.4. So this is your vector where you have added patches and their position embeddings. So this is how you perform position encoding, this step. So this is what we have done now, this step. So how we have performed this step? Each patch, so I have shown you this example for one patch. So if you are having 196 patches, so for each patch, and you will have a position embedding vector, and then you will add them element wise, and you'll get this kind of vector, 1D vector, and this will be your combined vector where you have the information about the patches, right, the features which are there in that patch, and you will have the position of that patch. Now these kind of combined patches will become input to the encoder of the transformer. Now we have prepared the input. Now that input will go to the encoder of the vision transformer. So now let's understand this transformer's encoder, right? So guys, first of all, in vision transformer there is no decoder. We only have encoder. Here also you can see we only have encoder, we don't have decoder. Why we don't need decoder? Because the task of decoder is to generate some sort of output, right? And in vision transformers, what we are doing, why we are using the transformers for computer vision task? What we want is, we only want to extract the features from the images. Okay, we don't want to generate anything. What we want, we only want to extract the features, and for feature extraction encoder is used, and we don't want to generate anything new, so that's why we don't need any decoder. Okay, so we are only going to use encoder. Now let's try to understand what is encoder and how it works. So first of all, let's understand what is the input to encoder. What is the input to this encoder? Patch plus position encoding, these kind of combined 1D vector will be the input to encoder. Okay, now let's try to understand the concept of encoder. Guys, if you'll see this side here, this is encoder, the encoder which they have mentioned over here. These are the layers. This is how the encoder of vision transformer work. So our embedded patches, the combined patches, here we have our combined patches. Combined patches means patches with the position embedding will go to the normalization layer, and then we have multi-head attention layer. Now let's understand the concept of this multi-head attention layer. Guys, this multi-head attention is the main layer which is which makes transformers special. So attention simply means where to put focus on, which part of the image is important, and model should focus on which part. All those kind of things are going to happen in this multi-head attention layer. Let's try to understand this concept with the help of example. Okay, so let's check this same example only. So suppose we have this input image, and this input image is divided into patches, and I am just taking these 4 patches so that we can understand the concept simply. Otherwise this entire image is divided into patches. So we have 4 patches over here. So guys, in multi-head attention layer, each patch, this patch, this patch, this and this, each patch have 3 tasks: query, key and value. So each patch will have these 3 tasks. What? Query, key and value. So we have given name to this patch is cat head, this is cat body patch, this is wall patch, and this is rug patch. Now all these 4 patches are going to have 3 tasks. What is that? They will perform query, key and value. Same for this, query, key, value. This patch will also perform query, key value, and this will also perform query key and value. Okay, now what is query key and value? So guys, query means that patch which is looking for other patches. Okay, so what query does, query sees that what all patches are there in our image to whom I should pay attention to, what all patches are there which are important to that particular patch. So suppose this cat head patch, when this cat head patch is working as a query, this patch will see that in this entire image what all other patches are there which are important to me, which are related to me. Okay, so this is what query does. And then we have key. See, then we have key. What key is? Key means the patches where we are where the query patch is paying attention. So see, here I've written also the patches which are matched with the queries. Suppose when the cat head patch is working as a query, this patch found this cat body patch related to it. So when cat head patch is a query, so this patch, this cat body patch will be the key to that query patch. Okay, and the value means the actual information which is present in that patch. Now let's try to understand this concept with proper example, step by step. So guys, for getting this query key and value for all the patches, we have 3 neural networks. Okay, so first neural network, this is a fully connected neural network. We have 3 fully connected neural network. First neural network will be used to create queries for all patches. So how many patches we have? We have 4 patches. So for these 4 patches, we will get the query value using this neural network. In the same way, then we have another neural network which is responsible for providing us the key for all the patches. Okay, for all 4 patches we will get the key using this neural network. And then we have a third neural network. This neural network is responsible for providing us the values for all the patches or for 4 patches. Okay, now let's see how it works. So these are the 4 patches we have. So first patch is the cat head, second patch is cat body, third patch is wall, and fourth patch is rug. So suppose we have these 4 patches, and for all these 4 patches we will generate query using, let's name it QH. QH means head of query patch, and QB means head body patch query, and here the QW means query of wall patch, and QR means query of rug patch. Okay, so this network will provide us this. And then for this patch we will get the key of head patch. For this patch we will get the key of body patch, and then we will get the key of wall patch, and we will get the key of rug patch. Okay, using this network. In the same way you'll get values. Okay. So QH means query of head patch, query of body patch. This is query of wall patch, query of rug patch. This is key of head patch, key of body patch, key of wall patch, and key of rug patch. Okay, now we have this. Now what is happening over here? So guys, this is the input layer, this is also the input layer, this is the input layer, these are the output layer of these networks, and in between we have hidden layers. Okay, and all these networks are going to use this formula only: y equals to wx plus v, y equals to wx plus b, and y equals to wx plus b, right? So y is the output. What is the output? What is the output in our case? If we are running this neural network, what will be the output? Queries, right? It will give the value of query for all the patches, and the output of key neural network will be the keys of all the patches, and the output of this neural network will be the values for all the patches. And how we are going to get? We are going to get using this formula, and we know the value of x. W, the value of W will be initialized randomly at the first stage. So guys, if you remember here in linear projection, let me go back to the example. See, the same formula we are using over here, Wx plus B, right? So this weight matrix will be learned during the training, and initially we put some random values, but this weight matrix will be learned during the training, right? And then we multiply weight with the input and we add bias in it, and we get the final values. See, this is how we get the final output of the neural network, right? So the same thing which we have learned over here will happen for query, key and value. And using these three networks, you will get QH, QB, QW and QR, which are the queries for all the patches. And using second network, you will get key for head, body, wall and rug. And using this, you will get the values for all the patches. So we have three neural networks and we are learning them separately. Okay. So the input to all these networks is same. What is the input to all the three networks? The output of the previous layer. And what is the output of the previous layer? Patches and their position embeddings. So if we'll see the same example, let's talk about these 4 patches only. Okay, let's not talk about the 196 patches. Let's talk about these 4 patches. Suppose we have 4 patches and each patch is of size 512, which means the input to query network, input to key network will be also the 4 patches of size 512, input to the value network will also be the 4 patches with size 512. So that means the input layer, this layer, right, this layer over here and this layer over here, the input layers are going to have 512 neurons. And now suppose what we want is, instead of having 512 values in all the 4 patches, I want to have 4 patches with value 64. Now after performing this query, key and value neural network, I want to have 4 patches. What we want? We want to have 4 patches and each patch should have 64 values. So that means the output layer will have 64 neurons. Let's say we are working on a query network. Okay, which neural network? The query neural network. And I've told you that each neural network will use this formula. Okay, and the input to all the networks is 4 patches of size 512, and the output we want is, how much output we want? What is the output we are expecting? We want each patch of size 64. Each patch should be of this size, right? And each input patch is of size 512 into 1, and each output patch we want of this size, right? And weight matrix, the weight matrix which we want to learn during this network training, the size of it will be 64 into 512, right? So this is, let's say this is WQ. WQ means the weight matrix for query. And in the same way, can we write like this? The input, which is patches plus position embedding, will go to 3 networks. First network will give us the query of all the patches. Second network will give us the key of all the patches. Third network will give us the values of all the patches. Here the weight matrix Q will be learned. Here the weight matrix key will be learned. Here the weight matrix value will be learned. And the size of each weight matrix is going to be 64 into 512, right? Here also the size will be 64 into 512, and here also, right? Can we write like this? Query of head, query of body, query of rug patch, and query of wall patch. All these queries value we will get from the query network, and these 4 patches are going to be 64 dimensional, right? The input will be the 512 dimensional vector, and it will give us the output 64 dimensional. In the same way, can we say key of head, key of body, key of rug, and key of wall? We'll get these values. The input will be the 512 dimensional vector, 1D vector to it, and the output will be the 64 dimensional. In the same way, we'll get it for it. So here we have 4 patches of 64 dimension. We have 4 patches with 64 dimension for queries. Here we have 4 patches of 64 dimensions for key, and here we are going to have 4 patches with 64 dimensions for values. So now we have, for all these 4 patches, we have their query values, right? We have the key values for each patch, and we have the value for each patch. Now how this query, key, and value work? So the query, suppose you're working on cat head patch. So when the cat head patch is working as a query, means QH is query of head patch, getting compared to the key of body, wall, and rug patch. In the same way, when you're working with this query value of body patch, when you want to see how much attention body patch should give to the head patch, wall patch, and the rug patch, at that time the query of body patch will be compared to the key of head patch, key of wall patch, and the key of rug patch. In the same way, when you want to check the similarity, or you want to see how much attention wall patch should give to head patch, body patch, and the rug patch, at that time the query of wall patch will be compared to the key of head patch, key of body patch, and key of rug patch. Okay, this is how it works. The query of one patch will be compared to the key of other patches. This shows how much attention should one patch give to the other patches. How much? Okay, so you'll see this kind of matrix. Now let's try to understand. See, we have 4 patches: head patch, body patch, wall patch, and rug patch. And over here also we have head patch, body patch, wall, and rug. Over here, query of head, key of head. What it means? Over here we are checking the similarity of head patch with the key of head patch only. We are seeing how much attention should head patch give to the head patch itself only. Okay, here we are saying how much we are comparing the query of head patch with the key of body patch, This means how much attention head patch should give to the body patch. Here the query of head patch and key value of wall patch. This means how much attention head patch should give to the key patch. Which key patch? The key of wall patch. Okay, in the same way, QH, KR, how much attention head patch should give to the rug patch. And in second line you'll see query of body patch. Here we are body, this line will tell the body patch how much attention it should give to other patches. In the same way, this line tells the wall patch how much attention it should pay to other patches, how other patches are related to it. Okay, what is the relation between the wall patch and the other patches? These all things meaning the same. Okay, all that we are knowing with the help of this. And in this line, the rug patch is checking how much attention it should pay to the other patches, how other patches are related to it. Okay, and diagonally if you'll see here and here, diagonally we can see we are checking the comparison, we are comparing the patch with itself only, we are comparing the rug patch with rug only, we are comparing the wall patch with wall only, we are comparing the body patch with the body patch only, right? So this is how the concept of query and key and value work. Now let's understand what will happen next. Once you get the values, these values, okay, what we are getting over here, we are getting the similarity scores. Okay, what we are getting here, we are getting similarity scores. Similarity score of this, similarity score between head patch and body patch. Here we are getting the similarity score between head patch and the wall patch. Here we are getting the similarity score between the head patch and the rug patch. Okay, in the same way here we are getting the similarity score between body patch and the head patch, body patch and the body patch, body patch and the wall patch. Okay, so this is how you'll get the similarity score for all the patches. So guys, here I'm showing you the attention score of head with the head. This is what I've shown you over here, right? QH into KH. QH means query of head, KH means key of head. Then we are calculating the similarity score, attention score between head and the body patch. Okay, this matrix, the first line. This first line I'm showing you over here. Okay, let's see here. See, so here I'm showing you, let's say for the first patch, okay, cat head patch, the query of cat head patch, we calculated the similarity with all these patches and these are the values we get. So let's say the cat head patch and the cat body patch, this and this, got the similarity score 0.7. and the cat head patch and the rug patch got the similarity score this 0.3, and cat head and wall patch have the similarity score of 0.01. Now the similarity score between cat head and the cat body is 0.7, so this is the higher score. Okay, so that means the cat head patch should pay attention to cat body patch, right? So guys, once you get the attention weights, so what we does is we transform those weights into the similarity scores using this softmax activation function. Softmax activation function provide probability values, right? So once you get the similarity score over here, once you get the similarity scores over here, we will convert them into once you get the attention weights over here, you will convert them into similarity scores. And how we does that? We does that using the softmax activation function. And suppose for the first patch, for this patch, this is the similarity of cat head patch with all the other patches, we got these kind of scores. We'll see which score is the higher. The score which is higher as compared to the other scores, that means this cat head patch should pay attention to that patch. That means this patch, cat body patch, is more related to the cat head patch. Okay, so this is how the transformer model learn about the image. This is how the transformer model learn the relation between the different patches and how these patches should be arranged in an image, and how all the patches are related to each other, and how much importance it should give to other patches. So all these kind of things are learned using this concept, the query, key and value, which I have shown you. So this is what query, key and values are. And after that, let's go back to the architecture. Here, this is an architecture. Okay, let's move to the over here. So now we know we divided the image into patches. This is the first patch. Then we flattened the image, right? Then we used linear projection on it. After that, we added the position embeddings, right? After this linear projection, what we have done? What we have done after that? We have performed this patch plus position embedding, and then you will get the combined vector over here. Those combined vector will become the input to the transformer. Under transformer, we have this multi-head attention layer. The output of this multi-head attention, what we are doing over here, I have explained you the concept of query, key and value over here. After that, we have this. What is this? We are performing addition over here. So the value, the vector which we have over here, we are adding that with the output of multi-head attention layer. What will happen with that? It will, like this, you can have the original information which was present over here, and then we are also adding the newly learned features over here. Then we are using the normalization layer. This normalization layer will normalize your data when you'll perform training. Means it will all the data will be in the same range. Okay, then we are using the multi-layer perceptron. Here our model is learning about the features. Okay, and then we are again using this addition over here, right? So that means the output which we have over here, we are adding that and the output of the MLP. Right, the current output and the previous output are getting combined, and then guys, you can use anything over here. For example, if you want to perform classification, you can perform classification. If you want to perform object detection, then you can perform that. So this is how vision transformer works. So I hope this video is helpful, and guys, if you like my content, please like, share and subscribe my channel. Thank you for watching.